we have particular types of functions, and the most trivial and maybe the most usual type of functions are called translations, rotation, and reflection. Here is an example of a translation. If you have the function f of z equal to z plus 1, then we have z is of course x plus I y, and we add this complex number z, which in this case is a real number, and we see that this u and v, the values u and v are x plus 1 for u, and it's y for this imaginary part v. So what does this mean? We started with some function z, which is x plus iy, for example here, and if we look at the expression for this function, we see that this function is translated in the real direction with the unit value. So each point in the domain of definition is translated 1 in the direction to the right. So you see that this is some translation. You see why this function is called a translation. Here you see an example of a rotation, f of z equal to I z. I is equal to the exponential function e in the power of I pi over 2, and we multiply this with z, which we can translate in polar form like this, and then we obtain this r multiplied with e in I pi over 2 plus phi. So what this means is that every point z is rotated an angle of 90 degrees. That's what's happening when you have this rotation function. So here we have an example of a function with a rotation, and here we have an example of a reflection. The function f of z, which is equal to the conjugate of z, is just equal to x minus iy. And you know that z is equal to x plus iy. So this point is transformed into this point. So we see that every point in the complex plane is reflected above the real axis. So this is therefore called a reflection. Well, here you see another example of a mapping. We have this function f of z equal to z squared, which we discussed earlier. You know that the real part of it is x squared minus y squared, and the imaginary part is 2 times xy. So let's just see what's typical points or lines where they are transformed into the function plane. Let's see what type of lines in the domain of definition which which has a vertical line as its image. And to do this, we just write u equal to some constant c1. And if we go to the expression, we know that u is equal to x squared minus y squared. So this guy should be equal to some constant. And to make this a constant is the same as describing a hyperbola. And this hyperbola corresponds to this vertical line. So let's see what's happening if we are considering the straight lines, the horizontal lines here. If we these lines are described by the imaginary part equal to some constant. So this v should be equal to some constant. And these type of lines in the complex plane also correspond to some hyperbola. Let's see what type they are. It's just these curves. So in this task we are considering the same function, and we want to find the image of this box, you can call it. All points described by this condition. X should be between 0 and 1, and y should be larger than 0. So what does this mean? Well, it means this this box, which is infinite in some sense. That's all points of in the set plane in the domain of definition. So if we let x1, say x1, be some number between 0 and 1, is some straight line here, what line does this correspond to in the range? Well, what we are doing is that we just write u, which is the real part of this function. It must be the x value, which is has this particular value x1, minus some arbitrary value y square. So x1 square minus y square. The v value, the imaginary value of the function, should be 2 times the x value, which is x1 on this line, multiplied with this arbitrary y value y. So let's just make the following trick, which is not so easy to find yourself, but just consider this. We just want to square this imaginary part, and then we of course get this equation. And now we see why this was a very wise thing to do, because when we have this equation we recognize y square, and y square is a part of the expression for the real part. So now we can replace y square or express y square in this equation by u or x1 square minus u, which we have done here. So then we arrive at this equation, and note that x1 is some constant. We have chosen a particular constant value, a particular vertical line here. So we obtain v square equal to 4 times this constant minus 4 times this constant multiplied with u. So let's just take some example. If x1 is equal to 1, then we get this equation. V square minus 4 v square equal to 4 minus 4u. And for example, if x1 is equal to 0, then we get y square equal to v square equal to 0. And these are hyperbolic functions. You see that this line describes this parabola, and for x1 equal to 1, and this describes the hyperbola for x1 equal to 0. It's just the point where v equal to 0, and u can be arbitrary. So we obtain all this. So what this means is that all points, let's go back to this box, this infinite box, all these points corresponds to all these points between x1 equal to 1 and this horizontal line. So all these points are mapped into this set. So let's consider the same function now, but a different type of mapping. Or we are mapping a different region in the domain of definition. So let's just write this set in polar form, and since we are squaring set, we can take the square of this polar form and obtain this expression. So, and this is really easy to see the image of, because here you see a typical set, and here you see the image of this set. The expression for it is like this. You see this point set gets a new value where the angle is twice the angle of is twice the angle of set, and the length of set is squared. So what does this mean? This means that if we, for example, have some circular domain like this, this will be mapped into this circular domain, and the only difference is that we have the angle, which is 90 degrees here, is 180 degrees here, and the radius is squared.